and welcome to E1's live webinar series on the design and performance of pressure sewer systems. We'll be covering part one in our two-part series for the next hour with a presentation entitled Avoiding Dangerous Curves with Pressure Sewer Systems. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. Before we get started, I do have some housekeeping notes. All attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of the presentation, as well as a certificate of attendance. And that's very important to note. I know a lot of people are always curious about that, so you'll get a PDF of the presentation and a certificate of attendance. And finally, we'd love to hear from you. We've allotted roughly 10 to 15 minutes of Q&A during today's session, so please make use of this time. Excuse me. If we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's speaker, Keith McHale, E1's Applications Engineering Project Manager. He's a seasoned E1 presenter, and if you've attended any of our previous webinars, you may recognize his voice. Today, we get to see his face. Keith is a professional engineer licensed in Maryland, Virginia, Connecticut, and New Hampshire, with 30 years in manufacturing and consulting engineering, focused in wastewater collection and treatment. As a consulting engineer, Keith's project involved evaluation, planning and design of wastewater collection systems, and treatment and disposal facilities. Keith, take it away.
Thank you, Rachel. Thank you all for attending today. As Rachel mentioned, today's webinar is what we call Avoiding Dangerous Curves with Pressure Sewer Systems. You do only get to see my face for the first few slides, and then I'm going to turn the camera off so we can focus on the overall presentation. I just want to kind of make as close as we can to making a connection here. So our agenda today is looking at pressure sewers and their development, kind of look at an overview of pumps in general for wastewater collection, a very brief overview. But we want to look at generally what pumps are used in wastewater application and why sometimes, in particular in the case of pressure sewer systems, it's valuable to go off script from that. Then we'll look at some of the pressure sewer design methodology and then kind of wrap it all up with some key points that are involved in pressure sewer systems that will tell us why the pump type matters on pressure sewer systems. And this is only part one, so next week we have part two, which is entitled Validating the Design Methodology of Pressure Sewer Systems. So today we're going to talk about two different types of pressure sewer system methodology, design methodologies. Next week, we're going to look at the design methodology for the semi-positive displacement pump and validate and explain where that development came from and validating it in more recent information. So now we'll start with a brief overview of pressure sewer systems. And as I do this, I will stop my video. So a pressure sewer system is a wastewater collection system that uses individual residential pumps to convey, grinder pumps to convey the flow to a treatment plant, a lift station, or can even be just discharged into an existing gravity sewer, either at a forced main or into a manhole. It's a very simple system that consists of individual grinder pumps located at each property and small diameter pressure pipes. Let's see, I'm not advancing. Okay, so with the grinder pumps, the solids from the residence or the commercial development, the solids are macerated down to very small particles, and this allows small diameter pipes to be used for the sewer main. Typically, that pipe is going to be about 2 to 4 inches. On some larger pressure sewer systems, you might see a 6-inch, in some cases, maybe 8-inch pipe. But for the most part, it's going to be 4-inch diameter or less. Unlike a gravity sewer system, the wastewater in a pressure sewer is pumped. So you don't need that precise slope and minimum pipe diameter of 8 inches that you would have for a gravity sewer system with a pressure sewer system. The pressure pipe can deviate horizontally and vertically. So that allows for a lot of flexibility in the pipe. Also allows for shallow installation. With the pressure sewer system, you're not excavating a deep trench with the constant slope that you would with a gravity sewer system. So you can install the pressure sewer just below the frost line. So not only does it allow for a shallow installation, but that installation allows for simpler and maybe more cost-effective construction means and methodologies, including low-impact cover if you were going to excavate a trench, or you could even use horizontal directional drilling because you don't have that critical slope that you have to maintain within the system. Now, I want to go over briefly a little bit of history of pressure sewer systems, and not so much on the early history, but kind of on the development of the E1 grinder pump. So the concept of pressure sewer systems is not that old. It really developed back in 1965. Harvard professor Dr. Gordon Fair was working on a problem that the Northeast and the upper Midwest and some areas had with combined sewer systems. You know, back then, there were a lot of combined sewer systems in many large cities and even smaller cities where you had the wastewater going into the same pipe as the stormwater. And this created a lot of pollution problems. So they want to address that problem by separating the pressure sewer system, by separating the domestic wastewater from the stormwater. And the concept that was developed early on was a pipe within a pipe, where you would have a small diameter pipe that would be located inside the large diameter combined sewer overflow pipe. And the concept was that the pressure sewer system would be suspended from the crown of the combined sewer pipe. Under the direction of what is now known as the EPA, the Federal Water Protection, Pollution Control Administration, and the American Society of Civil Engineers instituted a study to evaluate the options. And as part of this study, they embraced Dr. Fair's concept of establishing the concept of a pipe within a pipe with a small diameter pipe for the domestic waste that would be conveyed in a smaller pipe. Therefore, the materials had to be ground down. So what they looked at was establishing the criteria for the appliance to accomplish this task of separating the sanitary sewer from the combined systems. So where this led in their study was General Electric was contracted to develop this new household appliance. And why this little history lesson is important in today's webinar is this slide right here, where the GE team started with a blank slate. Their objective was to figure out what type of appliance, and this is the General Electric that was developed around appliances. So they were looking at this as an appliance. What appliance had to be developed that would allow for multiple pumps, grinder pumps, because you had to grind down, macerate the solids. What type of system would allow this to work properly? So it was a blank whiteboard, if you will. They were not a pump company that says, how do we make our existing pump fit into this system? They were a team that says, here's the problem. What do we need to do to develop that problem and solve that problem? And that team concluded that the progressive cavity semi-positive displacement grinder pump was best suited for this application. As we go through today's presentation, I'll throw, you'll see some examples and some reasons why this positive displacement grinder pump was viewed as being best suited for the application. And then down the road a little bit more, I don't know why the General Electric did not move forward with the concept, and the General Electric design team ultimately moved down the road a little bit and founded the Environment One Corporation. So when we look at a pressure sewer system, as I said earlier, it's a very simple system. You have the grinder pump that is located in the yard or the basement of each property. Wastewater flows into the basin from the building using the building standard service lateral. So this would be a typical 4-inch or 6-inch, whatever the code would require on a service lateral from the house to the sewer system. But instead of going to a gravity main in the street, this lateral now goes a shorter distance to the grinder pump basin. The basin contains the grinder pump with integral level controls. The pump is activated when the sewage in the tank reaches a predetermined on level and runs until it reaches the off level. So it operates in many ways similar to a traditional lift station, although in the case of an E1 grinder pump, it is a 1 horsepower pump that's operating for just a few minutes a day. So it's not really like a lift station. It is, as the GE engineers set out to prove, it's more of an appliance. So the runtime is short. Being a 1 horsepower grinder pump, the power consumption is low. In the case of an E1 system, the pressure level controls are determined by pressure level switches. So you don't have what you would typically as a flow tree within a lift station or even centrifugal grinder pump basins. So once the solids are ground up or ground down to small particles, the wastewater is discharged from the basin to the small diameter pressure main. So the pipe going from the basin to the pressure main will generally be about 1 1/4 inches. And as I mentioned earlier, once it gets into the pressure sewer system in the street, that pipe will generally be between 2 and 4 inches. And as I mentioned, in some cases, larger systems, you might see 6 inches. So when you look at a pressure sewer system, some of the advantages that you have is you have the small diameter pipes, and the shallow installation dramatically reduces the capital construction costs. This is done primarily through not only the cost savings of the smaller pipe, but you have much quicker installation. You're not digging as deep a trench, so the crews are able to install more pipe faster compared to a gravity sewer system. They're also not digging up the middle of the street to put that deep trench in that they would with a gravity sewer system. So you have less restoration costs and less overall disturbance. So the construction means and methods, in addition to the smaller pipe diameter itself, leads to significantly lower capital construction costs. We typically would expect to see between 40 and 60% cost savings compared to a conventional gravity sewer system. As I mentioned, one of the key advantages of a pressure sewer system is it can follow the contours of the land. So if you do have some areas where you might have to go uphill a little bit or deviate around other utilities or trees that you don't want to take off, unlike a gravity sewer system, with the gravity sewer system, your slope is constant and your alignment between manhole to manhole is constant. You don't have the flexibility that you have with the pressure sewer system to deviate from that. This allows for trenchless installation methods. Not only does that provide for maybe some quicker installation, more cost-effective installation, but it also disturbs less of the environmental surroundings. The other thing with pressure sewer systems is less impacted by underground utilities. Typically, in a utility, if there are all utilities in the utility corridor, the gravity sewer system is going to be the lowest. With the pressure sewer system, keeping in mind whatever code dictates on separation between water, sewer, and other utilities, you have that flexibility that if there are conflicts with other underground utilities, you're able to go around them more easily. And then one thing, it has lower, and then the last thing rather is it has lower social and environmental costs. This, as I said, with the means and methods, you're disturbing less of the community. You're not shutting down the street that you would with a gravity sewer, and you're not disturbing as much of the surrounding environment. It's a much smaller disturbance footprint. So this is, these last few slides are kind of the quick overview of pressure sewer systems. So we really don't have time to go into a detailed evaluation of some of the real advantages, other advantages in more detail. But certainly, reach out to E1 if you have any questions or if you're familiar with your local distribution partner. You can get more information on pressure sewer systems, as well as visit our YouTube channel that has other webinars and presentations that may go into some more of the details on the advantages and particulars of pressure sewer systems. Now we want to look at pressure sewer systems. A key part with the pressure sewer systems is you have independent pump operation. You have a pump located at each property, be it a residential property, an industrial property, or commercial property. And these pumps operate independently. They don't know what the other pump is doing. They don't sink into how the operation is going. So when we look at a pressure sewer system, and particularly the design of a pressure sewer system, it's important to remember that while there are many similarities between gravity sewers and pressure sewers, there are some key differences that must be considered in the design and operation of pressure sewer systems. In a gravity sewer system, the wastewater into the gravity main is an instantaneous process. With pressure sewers, the grinder pump basins act as a buffer between the wastewater generation at the property and the subsequent introduction of this wastewater into the collection system. Wastewater flows from the connected property to the grinder pump basin. The wastewater sits in the basin, and the discharge to the collection system is zero until the pump operation is initiated and the macerated solids are conveyed to the small diameter pressure main. So the peak flow factors that are typically used in the design of gravity sewer systems are not don't really apply to pressure sewers. Pressure sewer hydraulics are more dynamic than what we would expect with the gravity sewer system. And it's important to keep this in mind when we look at the design and operation of pressure sewer systems when we compare that to gravity sewer systems. So the heart of a pressure sewer system is your pump basin and everything inside the pump basin. You'd have one of these located at each property where you have your pump basin, your liquid level sensors, the components that tell the pump to turn on and off based on the liquid level within the basin, the pump controls that actually cause that function to happen, and then your pump removal guidance. So with this the E1 semi-positive displacement pump, that pump removal guidance is a little funnel where the pump just sits right in. Most centrifugal grinder pump will have a typical rail system that can create some operational and maintenance considerations they need to look at. But it's depending on the manufacturer, things might change a little bit, but they're all going to be basically the same component. The basin, some way to measure the liquid levels within the basin, the pump controls to turn it on off, and then a way to get the pump in and out of the system. Then, of course, you have the pumps. There are two types of pumps that are used in pressure sewer systems: progressive cavity pumps, which are the semi-positive displacement pumps of E1, and centrifugal pumps. And when you're looking at the design and the consideration of a pressure sewer system and what type of pump to use, it is important to really consider everything that would be involved. And that's why, the key point of a pump is the curve. And that is why my presentation is entitled Avoiding Dangerous Curves with Pressure Sewer Systems, because you want to make sure that the pump curve of the grinder pump is compatible with the pressure sewer system. So now we'll kind of step back away from pressure sewer systems and just look at pumps and wastewater systems in general. There are two main families of pumps in wastewater as well as water. These are dynamic pumps and displacement pumps. In more common terms, dynamic pumps are centrifugal pumps, whereas displacement pumps are actually more accurately referred to as positive displacement pumps. Both types of pumps have their best uses and best areas of application. It is important on any wastewater or water system to be able to identify when each pump type should be selected, which ultimately comes down to the working principle and the application at hand. Now, what I'm going to do as I go through the rest of the presentation is say that you want to look at the pump characteristics and what type of pump you would typically use in a particular application. But as we go through this, we're going to see that sometimes it's important to go a little bit off-label and use an application or use a pump that you would not normally expect to see in that application. It's important when you're selecting pump factors, in addition to looking at the general requirements of capital project parameters, such as the length of service, the capital cost, the operation and maintenance requirements. You also want to consider within any pump system, and particularly with a pressure sewer system, the nature of the material being pumped, the volume being pumped, any velocity concerns, if there's a minimum velocity or maximum velocity. And this is critical within pressure sewer systems because you do want to maintain a minimum velocity, if not for the successful operation of the system, because the code is going to tell you to maintain that minimum velocity. Part of that too is your total dynamic head or the system pressure. That as you have more flow going through a pipe, you're going to have more friction losses in addition to any static losses that you would have. So it's important to consider the system pressure. And then one of the things that's not often considered in wastewater collection systems is the viscosity of what is being conveyed. Because the viscosity for water is typically zero. For macerated solids in water is also going to be typically zero. But if you were pumping something like a sludge or some other chemicals or a polymer, the viscosity becomes an important consideration when you're looking at a centrifugal pump versus a positive displacement pump. So when we look at the two types of pumps, as I say, you have the two key families, the dynamic and the displacement. And then within those families, you have many subsets. With the dynamic pumps, you have centrifugal. And then depending on how the flow enters the pump impeller or how it enters the pump casing, it could be either actual flow or peripheral flow or a combination. And then on semi or displacement pumps, you have two primary means. It's either a reciprocating process or a rotary process, and I'll go into those similar differences and what they do shortly. But you can see you have your two primary families, but then you have subsets within those families. And generally, when we're looking at wastewater collection or any kind of conveyance of wastewater, it's going to be centrifugal. But as we go through this, we'll see that maybe there is value in using what you would not normally use, and that is using a displacement pump for the conveyance of wastewater, particularly wastewater in a low pressure sewer system. So going back to pressure sewer systems specifically now, as I say, you have two types of pumps that are used in low pressure sewer systems, centrifugal pumps and progressive cavity pumps. In our case, it is a semi-positive displacement pump. Centrifugal pumps are the most common type of pump found in water and wastewater systems. And how these work is you have the water that enters a rotating, or the liquid that enters the rotating impeller, and this imparts the rotational energy of the pumped fluid. The fluid enters the impeller of the pump by the rotating axis, or is accelerated by the impeller towards the discharge of the pump casing, the pump's fluid casing. Is greatly affected by the system pressure. A pump will operate where the system tells it to operate. So here, we say that centrifugal pump's discharge will be at the intersection of the pump curve and the system curve. Well, that's actually true for any pump system. Your system curve is going to be your total dynamic head. Your total dynamic head consists of any static lift you might have, and then your friction losses within the pipe. So that's, as you have more friction losses, your total dynamic head is going to go up. So your system curve is going to curve upward, as seen in the red line here. And the pump curve is fixed. So as that red line changes, as the dynamics within the system changes, the pump discharge is going to change. As I say, the pump will always discharge on its curve based on what the total dynamic head is. So here, when we look at this example of a centrifugal pump, we start with a static lift, which is the gray area. Let's see if I can. You have your hydraulic lift, but then you have your friction losses. So you can see in this example, under pump condition number 1, this is your system curve on the right-hand side. Now, think in a pressure sewer system, you have multiple pumps operating throughout the time. So every time a pump turns on, it's going to increase the friction losses in the system because you have more flow in the system. So as you have a higher friction losses, your system curve then moves up to this red line on the left. And what that means is when you have a lower friction losses, your centrifugal pump is going to be discharging at this intersection point, condition 1. Because you have more flow going into the system as grinder pumps turn on and on, centrifugal grinder pumps turn on and on. The total dynamic head is going to go up, and the discharge of the centrifugal pump is going to fall back onto this point of its curve. So the pump will always operate where the curve tells it to, based on the total dynamic head within the system. Now we look at positive displacement pumps. Positive displacement pumps operate by forcing a fixed volume of fluid from the inlet of the pump to the discharge of the pump. And generally it does so regardless of the system pressure. The amount of fluid displaced per cycle is dependent on the configuration of the pump. So we have different types of positive displacement pumps, but generally there is a void somewhere within the pump. And it's a plug flow operation that as the liquid being conveyed is pumped through the system, it's going to be the same volume. So it's going to move from one cavity to another or around one hose. And the system pressure on the outlet is not influenced very much based on the discharge volume. So with a positive displacement pump, as you have higher total dynamic head in the system, it's not going to impact the operation of the pump significantly at all. Again, when we look at positive displacement pumps, there are many designs, but they can generally be classified into 2 basic groups, and that is rotary pumps and reciprocating pumps. And you can see on the graphic on the right, underneath rotary and reciprocating, you have different types of these. These are gear, globe, screw, rotary vane, pure elastic, and then on the rotary type, it's a plunger or piston. So the reciprocating pumps move the liquid using one or more oscillating piston, plunger, or membranes in the case of a diaphragm, while valves guide the water or the liquid to the desired location. With a rotary pump, there are more positive displacement pumps that utilize a rotation movement rather than the reciprocation motion. They're designed to pump liquids, gases, or mixtures of two. And as the case with the reciprocating pumps, their capacity is based on the rotation. So every time the pump rotates, it will move a fixed volume of liquid. So typically in the wastewater world, we don't see a lot of positive displacement pumps. Usually, if you're familiar with positive displacement pumps on the wastewater or even on the water side of the industry, it's in an application where it might be a sludge or a polymer, or something that is a little bit thicker than water. So where you would typically see the application of a positive displacement pump is areas where you might have a high pressure, low flow. They're usually more effective in operating against high pressure and low flow applications. Although centrifugal pumps can be designed to generate high pressures, the use of multiple stages, these special pumps tend to be comparatively expensive. So if you do have a high pressure and you're going to go with a centrifugal pump, that would tend to be more expensive than if you just have a typical lower pressure and go with a standard centrifugal pump. Another area where you would typically see the use of a positive displacement pump is in high viscosity. With high viscosity, that's the how easily a fluid moves through a pipe. So positive displacement pumps are more effective than centrifugal pumps in moving viscous fluids. Really, in the wastewater application, you don't really see anything that's viscous. As I mentioned earlier, you might see like a sludge or a mixed liquor suspended solids or a polymer. We tend to have a higher viscosity, so it's going to take more energy to move that liquid or that liquid through the pipe, because the pipe has a the liquid has a tendency to hold on to the sides of the pipe. So you need a little bit more power. Another area where you typically see positive displacement pumps is when you need accurately controlled flow. Since each stroke or revolution generates a certain amount of flow, the positive displacement pumps are typically used in applications that require this precise flow, such as a chemical feed, or if you want to discharge the same volume of material, liquid, each time it goes on. And then what we're going to focus on now is what I would call the operational advantages, that even if your application doesn't fall into one of the top three bullets there, the high pressure, low flow, high viscosity, or accurately controlled flow, there might be an operational advantage to using a semi-pod or a positive displacement pump. And that's where we're going to go back now to the grinder pump application and look at E1's semi-positive displacement pump. So one thing I will say, up to this point, I've been talking about positive displacement. Now, when we get to the grinder pump application of it, I'm going to change it a little bit. We change it a little bit to a semi-positive displacement, because what you have with the positive displacement is, because if you have a high viscous liquid, you don't have a lot of it slipping back from the outlet to the inlet. But with the semi-positive displacement pump, and this is a rotary version of a typical, if you recall that family tree, this would be a rotary version. So you have the material that is ground up, and then you have a stainless steel rotor and a stationary elastomer stator. And as the rotor rotates, it takes the wastewater and the ground materials, and it creates a series of cavities that moves the fluid from one chamber to another chamber. And as I said, it's a plug flow operation. So it will discharge the same volume as it goes through here, regardless of what the system pressure is. It is going to fill this discharge line with the liquid based on moving one plug of water into the next chamber, and then keep moving that plug through these chambers. Now, why we have a semi-positive displacement application is the overall design of this pump would be a positive displacement. But because we are conveying basically wastewater, we're grinding up the solids, but the solids within the wastewater component of a pressure sewer system has a viscosity very similar, if not almost exactly the same, to water. I think water has a viscosity of 0, and if I remember correctly, just to give you a point of reference, toothpaste has a viscosity of 200,000, what is known as sapois, the way you measure viscosity. So here we're moving essentially water. And because that wasn't the way this is necessarily designed for, you do get a little bit of slippage of that water. That's why it's semi-positive displacement and not full positive. But what this does is it produces a constant flow that is only marginally affected by the system pressure on the discharge. That yields a system curve that is near vertical. Now, if we were looking at a truly positive displacement pump conveying, say, a sludge product, some mixed electric suspended solids or something like that, or any fluid that had a higher viscosity, this pump curve would probably be a little bit more vertical. But because we are conveying a liquid, we do have that slip. So we do have some variance that if you do have a higher pressure, you are going to get a little bit more slip through this cavity than you would with water. But it is essentially a near vertical curve that, with very little variation, regardless of what the total dynamic head is in the system, you're not going to have as much variance on the discharge point of the curve. So where this becomes kind of important, you have your pump curve comparison. As your system head goes up on a centrifugal curve, depending on what your total system head is, you're going to discharge some point on your centrifugal curve, either a high discharge or a low discharge if you have high pressure. But with the semi-positive displacement pump, you're going to be discharging essentially the same flow from that pump every time. Then as I go through the rest of this presentation, I want you to kind of keep this graphic in the back of your head to kind of remember the comparison between these curves. So when we design a pressure sewer system, there are two design methodologies. The rationale method, which is also known as the peak effluent flow method, and this is generally applied to systems using centrifugal grinder pumps. But the rationale method can also be applied to systems using semi-positive displacement pumps. I don't know that there's a real good reason to do that, but you could use this rationale method on a SPD pump. Then we have the probability method. This method is also known as a simultaneous operations method. And this method only applies to systems using pumps with a near vertical pressure head discharge curve. And that is because you want to know exactly or have a good idea on what that discharge is going to be with the probability method. So just kind of quickly go over these. The rationale method proposes that the design flow would correspond to the number of homes served within a pressure sewer service area. It is based on the assumption that each pump that is running will operate at the discharge flow based on the pump characteristic curve and the total dynamic changes in the pressure sewer system. So again, going back to that centrifugal curve, as you have changes in your total dynamic head, the discharge is going to be a point on that pump characteristic curve that corresponds with the intersection of the total dynamic head or the system curve. The pumps are selected based on the needs to discharge into the main at an acceptable flow rate given the system pressures. So when you're designing a pressure sewer system, or using a centrifugal grinder pump, on one part of the pressure sewer system, you might have centrifugal pumps that are sized differently or have a higher horsepower or have an impeller trimmed so that they meet the anticipated total dynamic head within the pump's best efficiency point. The rationale method is pretty straightforward. It is a linear equation. It is given by the formula you see here. Q, the discharge, the design flow of the pump, is the product of the coefficient selected by the designer, which includes the number of pumps running simultaneously. This value will typically be 0.5, and the product of the A, as well as the number of equivalent dwelling units, or the number of pumps in the system. So you have your coefficient times the number of pumps in the system. Then you have this adder, which is the baseline flow B, and this is the anticipated flow of one pump discharging into the system. So you always have this minimum flow. So that value is typically going to be 20, which would be 20 gallons per minute for centrifugal pumps, or 11 for semi-positive displacement pumps if you were to use the rationale method for semi-positive displacement pumps. So it's, like I said, pretty straightforward application. Just takes in the flow is based on the number of connections and a couple of parameters there. associated with the number of pumps operating simultaneously. Now, when we look at semi-positive displacement pumps, we look at the probability method. This is also known as a simultaneous operation method, or you might see that shortened down to SIMOPS. And we're going to go into a lot more of the simultaneous operations on next week's webinar. But simultaneous operation is a widely accepted methodology for designing pressure sewer systems, especially sewer systems employing low horsepower, semi-positive displacement grinder pumps. This method proposes that the maximum flow will be dependent on the number of pumps and the total population of pumps expected to be operated simultaneously. A key assumption with this is that with the probability method is that the discharge from each pump will not be significantly altered due to the changes in the system's total dynamic head. So with the probability method, you look at the number of pumps that are in the subset or the system. So here, if we're looking at, say we have 40 pumps within the section of the pressure sewer system, the expectation is that no more than 6 pumps will be operating at any given time. And when you design pressure sewer systems, much like when you design a force main or gravity sewer systems, you're sizing the pipe to optimize the friction losses. So you want to make sure that the pipe is big enough to convey the peak flow, but small enough so you maintain the proper velocities. When we look at the probability method, as I say, it's based on the assumption that every pump is going to discharge the same thing. And that's why it really only applies to semi-positive displacement pumps. Because here we say, I'll use another number here. If you have 12 pumps operating, the expectation is that no more than 4 would operate at any time. And you know that those 4 pumps are going to discharge somewhere along here between 9 and 11 gallons per minute. So if we call it 10, if you have 4 pumps operating, your discharging into that system is going to be 40 gallons per minute. So it makes it very simple to kind of go through. And again, I'll reference you if you want, this doesn't go into a lot of detail. So we do have some videos that go into more detail on actually designing the system, but this is the overall methodology. And what we see with this is there's not a lot of differences. If you look at the curve, the red curve, which is the rationale method versus the semi-positive displacement of the probability method, they're very similar, particularly if you're looking like 200 to 300 connections, which is a typical pressure sewer system in our experience. So you don't see a lot of variance in what that discharge is going to be. And as I say, when you're designing this, as when you're designing anything, you're kind of using the best information you have to select the best product. At the end of the day, we don't know what that flow is going to be. We don't know what it's really going to be. So we want to estimate it. And here's kind of what I call the unspoken truth. And you'll hear other manufacturers, question the probability method. How do you know how many pumps can be operating? Well, with any pressure sewer system, whether it's semi-positive displacement pumps or centrifugal pumps, the probability of multiple pumps operating simultaneously is common to both methods. Under both design methodologies, the grinder pump acts as a basin. The wastewater enters the system only when that pump turns on, and when that pump turns on, it introduces more flow into the system, and that creates an increase in the total dynamic head. So recall, the pump discharge is based on the intersection of that pump curve and the total dynamic head. So with the pressure sewer systems, you have a lot of variance with that total dynamic head, and it's all going to be controlled on how many pumps turn on at any given time. Doesn't matter if it's a centrifugal pump designed with the rationale method or a semi-positive displacement pump designed with the probability method. So a couple things to consider. E1 recently completed an evaluation looking at 66 grinder pump sites over the course of 6 months. We want to look at the total cycles per period, average cycles per day, and the total average run times. And what we found was kind of what we knew, but this kind of gave us the confirmation. Typical residents will cycle on and off 19 times per day. The average runtime is only 43 seconds with a calculated wastewater flow of 150 gallons per day. So what this tells us is you have pumps that come on and off at various times for very short periods. So you have that very dynamic operation within the pressure sewer system. You have a pump that comes on, another pump comes on, but while that pump is on, the one that was already on for 30 seconds turns off, and you have more come on and off. And they come on and off at different places within the system. So we want to look at the distribution of the pump operations. Raises a couple questions. We have grinder pumps located at each property that are going to come on and off and operate for just a short period of time. Is the distribution of these running pumps a design concern? And what happens if you have a large percentage of the running pumps that are initially located, or that are the initial part of the system that are located in one specific zone. They're all kind of consolidated together. Does that create any design or operational problems? So to answer these questions, we go to kind of the standard probability equation. You take into account factorials that looks at the number of operating pumps, M, out of the larger pump population in the system, N, is given by this formula that looks at factorials. So we'll look at that. So for example, if we're looking at 7 pumps, we have a sub-basin of 75 pumps. Based on our probability analysis, we know those 75 pumps, no more than 7 would be expected to be operating simultaneously. So if you take that 75 as N and that 7 as M, plug it into the probability equation, you can see that the probability of these 7 pumps being concentrated in one localized area is very, 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 very small. It is more probable occurrence is that you're going to have an uneven distribution of the running pumps throughout the system. Those 7 pumps will be spread out throughout that entire 75 residence sub-basin. So you're not going to have a consolidation of flow, and you're going to have a very wide distribution of the flow. Another thing to consider with pressure sewer systems is the pressure and the dynamic of it. So this is a graphic from a study that an engineer in New Zealand did a couple of years back that they shared with us, where they looked at the system pressure within an E1 system. And you can see this is the daily pressures within this section that they were monitoring. You can see some definite spikes. But let's look at a tighter version. So here we're looking at just one day. And these little tick marks are 2-minute increments. So the tick marks down here are 2-minute increments. And you can see that with the semi-positive displacement pump, you have some pretty big variances of the total dynamic head over a very short period of time. So here we're looking at, 6.4 bar, 5.5 bars, not 6.5 right the first time, 6.5 bars of pressure. And then within a minute or a couple of minutes, it drops down. So within about 15 minutes, you have this big drop in pressure, then it goes up and down. So you can see very dynamic with the semi-positive displacement grinder pump within a pressure sewer system. We see the same thing with centrifugal pumps. So this is from a report entitled Aspects of Pressure Sewage System Design that was drafted in 2015. And here the author did an evaluation of pressure sewer systems that had centrifugal pumps. And these is the timeline versus the total dynamic head. And you can see the same thing. You have very high changes in your total dynamic head over a very short period of time. So with this 1-minute increment, your pressure drops quickly or goes up high, and you have a lot of variance. And what this is these are changes. This is these lines are the total dynamic head. So you have that variance within the system. So that's why going back to this curve, where we say the pump curve matters, where you have, your total dynamic head, these horizontal lines here are pump operations. So you have more pumps come on, your total dynamic head is going to go on. With the centrifugal curve, a stroke curve, you're going to be operating over here, but then one pump turns off. So your total dynamic head goes down, and you're constantly riding the pump curve. You're also riding the pump curve with a semi-positive displacement pump, but your discharge from that pump does not have as much variance. You're always going to be on what we would term the best operation point. Whereas with the centrifugal pump, your best operation point would typically be about here. But there are going to be times in the pressure sewer system with centrifugal pumps that you're going to be operating on the left-hand side of the curve where you might have some recirculation problems, or the right-hand side of the curve where you might run into some cavitation problems. So here we're looking at the frequency of pumps turning on and off and what that does to the total dynamic head. Another thing that we can consider when we're looking at the benefits of a semi-positive displacement pumps is what we would call the self-scouring behavior. Here, we're looking at your standard continuity equation. The velocity in a pressure pipe is directly proportional to the flow and inversely proportional to the cross-sectional area. The velocity is given by the equation Q over A. So with the pressure sewer system, and it doesn't matter if it's a centrifugal grinder pump or semi-positive displacement pump, you're going to get some sedimentation that may begin to settle in the pipes. One thing we got to keep in mind, as I said, mentioned earlier, the pumps operate for a very short period of time. Generally, a household grinder pump will operate for no more than 20 minutes per day. So this isn't a pressure sewer system is not like a wastewater force main or a water system where you always have that pressurized flow in there. There are times when you may not have any flow in there, so you might have some sediments that settle. And it's not really concerned with semi-pod displacement pumps, because what we see is as you have settlement within the pipe, the cross-sectional area is reduced. If the flow is near constant, you have this reduction in area. If the flow Q remains constant, you're going to see an increased velocity to the pipe. That increased velocity is going to equate to increased friction losses. And that's why, again, the pump curve matters. As these obstruction creates resistance within the pipeline, you have a smaller diameter where the flow is moving, so that's going to increase higher friction losses. When you have higher friction losses, you move up your system curve, and then you're going to move again, as I mentioned many times, on a centrifugal curve, you're going to move to the right or left, depending on what happens there. But with a semi-pod displacement pump, you're going to stay pretty stable. And what this does is eventually over time, if the pump curve has a large horizontal range, it's going to cause the system pressure to go up. But if you have that semi-pod displacement pump and you have that reduced area, you're not going to have a reduction in your flow. With a centrifugal pump, as your total dynamic head goes up, the centrifugal pump is going to move to the left-hand side of the curve. It's going to discharge less flow. So it's going to adapt to the system. The Q is going to go down, the V is going to go down, the velocity is going to go down. Therefore, you're not really going to address this sedimentation problem. But with the semi-pod displacement pump, you're not going to really go down on your discharge. Therefore, your Q is going to remain, your flow is going to remain essentially the same. And if your flow is the same, your velocity is going to go up. And eventually, you'll get to a point where that velocity and that flow will resuspend any settled solids and then move it down the line. So when you look at a centrifugal pump versus a grinder pump, and you have the potential to have some solids settle within the pipeline, you can see that, again, the pump curve matters, that because you're not having a lot of variance in your discharge flow that is driven by the total dynamic head, you're able to control that behavior. So when we look at the design methodologies, as I went through there, you look at the pressures within the system, the number of pumps coming on and off at various times, the short amount of time those pumps that do come on, how long they operate, only 43 seconds on average, they're typical. And you don't have that flow throughout the entire day. So the system design methodologies, when you're looking at the two types of design methodologies based on the type of pump, they differ, but certain operational parameters are the same. And the key one being the total dynamic head and where the pump discharges based on the pump characteristic curve discharges in relationship to that total dynamic head. So the system design method isn't not as important as the pump selection. If you recall back to that one graph where I overlaid the two things, the estimated flow from the two methods is going to be very similar. But the operation of the pump based on the type of pump that is selected does have a much bigger impact on it. So the hydraulic conditions in the pressure sewer can be very dynamic and highly unstable. And that's where, going back to that history slide, that's where the developers of the semi-pod displacement grinder pump that ultimately became the E1 grinder pump, that's where they saw as the appliance of developing the right product or modifying it, in this case, modifying a product that's normally used for sludge conveyance, modifying it to a wastewater conveyance, more of a liquid planes, because the key advantage is that curve. That curve matters when you look at semi-pod displacement pump versus centrifugal pumps in a low pressure sewer system. Now, a little bit of teaser. Hopefully I got you interested in some stuff. I mentioned the probability method and even the rationale method. Both of these design sewer methodologies were developed just over 50 years ago. Pressure sewer systems are a very new concept, especially when we compare it to gravity sewer systems. So part two of our webinar series, which will be next Tuesday at 2:00 Eastern time, we'll go into the methodology of pressure sewer systems for semi-pod displacement pumps. And there we'll talk about the development of the probability method, and then how the technology has advanced in terms of flow monitoring, and the increased number of grinder pump connections has increased tremendously in the last 50 years, and how these two events have provided E1 the opportunity to go back look at the development of the probability simultaneous operation method and validate it that is still an acceptable means to design pressure sewer systems using semi-positive displacement grinder pumps. I think my time is pretty good, so hopefully we have about 12 minutes of questions.
Yeah, I'm coming in with about 10 minutes here, Keith. Hey, thanks for that excellent presentation. And just to address a few questions that have come in right away from our attendees. Yes, you will receive a certificate of attendance for attending today's session. And you will also receive a link to download a PDF of Keith's slide deck here. So look for that in your inboxes probably tomorrow morning, realistically, and you can have fun with all those items. But right now for some questions. Keith, are you ready?
I am ready, Rachel.
Okay. First question, do you have a sizing tool available for unique applications, such as an RV dumping station, shower house, or other?
I would say that's probably a very timely question. The short answer right now is no. We do have ways that we do that. So if you do have that application, certainly reach out to E1 or to your local distributor. But I will say we do have a tool in development. So right now, if you were to go to E1's website, we do have a design assistant tool to design pressure sewer systems. We do have something in development that we should be ready to release within a couple of weeks, actually. So right now, if you were to call the factory, we could help you with that. But we might even be able to get you kind of an early release of that tool that would look at what we call commercial or multi-residential applications, and that would be exactly what the question asked: RV parks, businesses, gas stations, any of those establishments. So to kind of wrap that up, I kind of went all over the place. We can help you with that right now, and we will have a tool available to you in the very near term.
Does the rational method have an upper limit on number of units connected?
I have never seen anything on the rational method. As Rachel mentioned in my introduction, I was a consultant engineer for several years. So I designed pressure sewer systems. Going back to the late 80s, early 90s, I called up to the factory and said, how do you design this system? So to me, the semi-positive displacement, I don't say this as someone who works for E1 now, but as an engineer going back 30 years, 20 years, the semi-positive displacement pump always made sense to me when you have a couple hundred pumps operating simultaneously. So my design experience in my consultant days, I've always used the semi-positive displacement pump and the probability method. So I don't have direct experience with the rationale method. I have researched it, I have looked into it from a comparative, and I haven't seen anything that would say that there's an upper limit. I think once you get up to a higher number, it's a linear thing. So you might be over designing the pipes in some sections, but there could be an upper limit, but I don't know that it's too critical for what you're looking at.
Check valve immediately head of tie-in to force main manifold. If you have a multiple grinder system, recommended.
I'm sorry, Rachel, you broke up on the first part of that question.
Did I? Okay, sorry. In a separate, is a separate check valve immediately ahead of tie-in to force main manifold on a multiple grinder system recommended?
Yes, absolutely. We would recommend a check valve at the property line where you tie from the property into the pressure main. There's also with the E1 system, there's an integral check valve within the pump core itself. So we would actually be recommending kind of redundancy, but it is a good design practice to install a check valve at the property line. In fact, we have a unilateral valve that has a check valve, an inspection port, as well as an isolation valve. So you can isolate, one, you could prevent any flow from the main line going back into the service lateral, but you could also isolate that flow if you had to take the pump out of service, or if you had to take the line out of service, or if you have you install your mainline pipe first before you install your individual grinder pumps.
And we've had several questions come in related to this. So what happens if there is a power loss at the property with the grinder pump connection?
Well, there's a couple things. I never like to minimize people's experience with power losses. We all remember that one event where we lost power for a couple of days or a couple of hours. But when we look at the national grid in reality, power losses are not as significant and not the biggest fear of that one event we all remember. For me, it was the ice storm of 08. Lost power for 3 days. But one thing we see, and this is third-party reports, when you lose power, your water consumption is going to drop down. You're not going to run your dishwasher. You're not going to run your washing machine. Any wastewater generating rather, utility appliance that uses power, you're not going to really use. Depending on how your hot water system is, you may not want to take, the ice storm of 08. It was a couple of days before I took a shower because I didn't want to take a shower with the cold water. So water consumption does stop. Now, when pumps come on, this is another thing that's kind of an advantage of a semi-positive displacement pump compared to a centrifugal pump. When the pump comes on, you might have all the pumps turned on at the same time. So with a centrifugal pump, that's going to be a lot increase in your total dynamic head, which is going to move you to the left-hand side of the curve. So you're going to have a much smaller flow from those pumps that are able to enter the system because of where they're going to be operating on the pump curve. With the semi-positive displacement pump, it's also going to have a higher total dynamic head if pumps try to enter, but it's not going to be deadheaded. So you don't have that deadheading pump that you have with the centrifugal pump. We have a thermal overload. So if it's running against the pressure that it cannot enter the system, enter the main line, the thermal overload will trip. It will turn the pump on, and then the pump would try again in a few. I don't know exactly what the time frame is, but the pump will try again. And again, keep in mind. The pumps operate at different times. So when you lose power, not every pump was ready to discharge. So not all going to be trying to discharge when the power comes on. And when it does come on, they only operate for 45 seconds or less. So it doesn't take too long. And it doesn't really create a problem. Now, if you are concerned with that, we do have alternatives to have a generator receptacle or a means for emergency power to the grinder pump. And again, if you are concerned about that, talk with E1, talk with your local distributor, and we can show you some of the applications of incorporating a generator outlet into the grinder pump.
Have you or someone done a comparison between E1 systems or SPD pumps and vacuum for cost and maintenance, life cycle, et cetera?
Yeah, it's a pretty good question. We have looked at it from a technical level. We actually have developed a life cycle cost calculator, which you can find on our website. I apologize, I don't know exactly where on our website, but I think if you go to e1.com, particularly in the SSB.
It's in our design center, Keith.
Thank you. SSB in the design center. We have a cost calculator where you can actually do a life cycle cost analysis, looking at the capital cost, as well as the operation and maintenance cost of gravity sewer, septic tank effluent pump sewers, and vacuum sewers. And this model, has some parameters in there in terms of what would be reasonable, but you can change every parameter to meet the conditions that you're working with specifically. And when I have looked at other reports, and if, I'm not sure who asked the question, but if you were to email me at if you were to email me at kmckel.com, I do have some third-party reports where engineers did an evaluation of various types of sewer systems. And we find in most cases that, as I mentioned earlier, 40% cost savings compared to gravity sewers. And I don't know the exact percentage, but typically these third-party reports did show a cost savings of pressure sewer systems compared to vacuum sewers. And when they did the analysis of pressure sewer systems, they did not necessarily have a breakdown of centrifugal versus SPD. It was just pressure sewers themselves.
Okay. What is the minimum number of houses needed to make the system work?
One. A pressure sewer system, particularly an E1 pressure sewer system, can be as small as you want or as big as you want. It is not uncommon to have one grinder pump that is discharging to the end of the driveway into the gravity main. We have some projects where a gravity sewer system, I have one up in Oakland County, Michigan. I believe off the top of my head, I think it's 14 houses that were discharging into a gravity sewer, and during storm events, the gravity sewer became surcharged and the wastewater would back up into the basements of the homes. So on this project, they install on these 14 houses, they install an E1 system that discharges right to the end of the property line into the gravity sewer system. So when that gravity main becomes surcharged because of the excess infiltration and inflow within the system, not only does it keep the water from flooding the basement, going back up the lateral into the basement, but the grinder pump has the power, the E1 grinder pump that can discharge up to 85 feet, has the power to discharge into that surcharged gravity main. So it could be one pump, could be thousands of pumps.
Well, Keith, thanks again so much for this presentation. And folks, we have about 47 unanswered questions that we'll be following up. I know.
I guess I know what I'm doing this afternoon.
No, your diary is booked. So we'll be following up with an email with the answers to your questions there. And on behalf of all of us at E1, we thank you so much for joining today's session.